Hey guys, Dr. Callahan here. Welcome to week 4, Friday for Calculus AB for semester 1. Go ahead and pause the video and start your 3 questions for your warm-up log. All right, let's go ahead and see if you're the top 8% of the smartest people in the world. I'm not sure if I believe this, but see if you can find your name. I hope you found your name. All right, let's go ahead and take a look at the last example here. This is the one that says as limit approaches 0 for 5x over sine 5x. Initially, if you go ahead and do direct substitution, sine of 0, if you plug that into your calculator, is going to give you a undefined, okay? Because it's a result with a 0 in the denominator, which is undefined. So then what you can do is, since you cannot analytically do this with algebra, so that's a big no-no, there's really nothing that we can do, there's 2 additional methods that you can try with this. Number 1 is with graphing, and the second one is with a chart. So if you attempt to do the graphing, you would technically have to have a TI-84 calculator unless you can graph this in your head. I can't, but maybe you can. But if you do go ahead and graph this, this is what it will look like. And if you take a look at this as x approaches 0, you can see that it has 2 different responses for y, which is the oscillating, so it does not exist. On the other hand, if you try graphing it, here is my chart. I can go ahead and try a few numbers that's close to 0. So if I try -2 on the left side, +2 on the right side, you can see that -2 results in a -18, -1, which is still close to 0, all of a sudden jumps into a -5. And there's just a really big gap in between. I mean, it's not being consistent. You know, as x is approaching 0, it's not approaching one definitive number. Now, on the other hand, you can try something even smaller. You could try -0.001, -0.5, -0.9. And as you get close to the 0 from the left side, you can see that it's jumping from a -2, the y value is a -18. From a -9, it's a -4.6. From a -0.5, it jumps all of a sudden to a +4.2. So this is where it's kind of dipping down and then oscillating up and then dipping down. So because there's no consistency in either of the methods, it does not exist. It is oscillating. So if you have a question that involves a trig function such as this, I will suggest that you probably use your calculator to create a set of tables, or a set of values with the tables. You guys had 6 questions on your, or 5 questions on your guided notes. These are the answers to them. Some of them you can just do with direct substitution, like this one right here. 5 times 4 is 20, plus 2 is 22. With number 1, you would have to factor out the top into a x minus 3, x plus 2. On the bottom, x minus 3 cancels, and then it's just going to be x plus 2, so 2 plus 3 is going to result in 5. We went over number 3 together. This one, you would have to go ahead and there's nothing to do analytically, algebraically wise. So you would have to create a table of values, but even with a table of values, you're going to know that it's going to become does not exist. With number 6, you would have to factor the top with the cube factorization of a cubed minus b cubed equals a minus b times a squared plus ab plus b squared, and just factor that way. And eventually you'll know that the denominator x minus 1 will cancel, which will result with an actual answer on top. Yesterday, we did talk about discontinuity. All 3 rules must be met in order for a limit to be continuous. So that means as x approaches a from the left side, as x approaches a from the right side, as x equals a, the f of x or the y value have to have the same consistent number in all 3 cases. This was your answer to your calculus puzzle. It says, what did the asymptote say to the removable discontinuity? Don't hand that holier than thou line to me. Haha. These are my notes that I went ahead and typed up for you guys that summarizes part of our lessons. It is the same skill set. So like we talked about continuity. So my notes focuses in on continuity. I rather prefer to focus in on going over examples in class because we have so much materials to cover, you know, in this, I guess, hybrid schedule. It's a lot of material to cover on a regular schedule when we have only 180 days of the year, and your test is in May. And with this year, with a hybrid model, I only see you guys half time. So we cannot just forego some of the skills. I don't ever reteach the same lesson, even though I might not see you guys the following day. I just continue on with my videos. So if I'm presenting this lesson to you guys in person in class, the same video is presented to the other class online because they're at home. And the following day, I'll go move on to the next lesson. But these are the three different type of discontinuity: removable discontinuity, non-removable discontinuity, and then removable discontinuity. So these are the three different types. All right, let's go ahead and take a look at our focus for today. Today, we're going to talk about special trig limits. I'm going to go over the 2 examples in your guided notes. In addition to that, I have section 1.3, which is evaluating limits analytically. Section 1.4, continuity of one-sided limits. I do have a video on the guided notes, which is a summary on everything that's limit related. And then I have one more calculus limit puzzle. And it says, what did a college freshman who failed his first calculus test have in common with a college freshman who was fined for driving 60 miles an hour in a 30-mile-per-hour zone? Such a math question, goodness. All right, so with that said, let's go ahead and continue. If you would like to go ahead and pause the video and go ahead and go over some of these examples on your own. It is organized. I always try to go over one topic at least 2 days because calculus is hard. The first day that you're introduced to it, it might just be trying to soak the information in. You might not understand all components of an example, but I feel like the second day that you're introduced to it, you still remember some of the key concepts from the previous day. And so it just sinks in a little bit easier and it all of a sudden just clicks. And so this is the second day that we're going to be spending on limits. Also, if you would like to go over the steps, I have this link right here. It says https://tinyurl.com/hcp73z as in zebra and 5. If you type that in, it'll take you to a video which actually covers these questions step by step as well. And these questions are from the textbook. So I try to give you guys like a wealth of type of questions. We have different questions from Math Excel. We have questions from AP College Board, questions from the textbook, questions that I have pulled from Barron's AP study guide for calculus. And so we have a variety of different questions. All right, so let's go ahead and take a look at some of these examples. So go ahead and turn over to your guided notes on the video. And we're going to go ahead and talk about this example right here. Actually, it's not really much as an example as just special trig limits. I will highly suggest that you guys memorize these because the sooner you memorize them, the easier it will be for you guys to actually do the limits. You will realize that the difference between calculus and pre-calculus and trigonometry is that in this class, you have to memorize all of the formulas, unfortunately. On the AP exam, they do not give you anything. It is simply all by memory. So looking at the first one, this is a special trig limit. So as sine x over x, as limit x approaches 0, it is always going to be 1. And if you don't believe me, we can create a table of values. And you can kind of try this out yourself. I could say that x approaches 0.01 on the left side. I can say x approaches positive 0.01 or positive 0.1, so it's getting closer to 0 or further away, I guess in this case. It's me 0.9998, 0.9983, 0.9983, and actually this one has 3 nines. There we go. So it's pretty consistent. And I can go ahead and say that this is going to approach 1. And if you memorize this, awesome. The next one, special trig limit, is the limit as x approaches 0, 1 minus cosine x over x. It is going to be 0. All right, let's go ahead and using these 2 special trig limits, let's go ahead and approach question number 70. Oh, no, I don't want this. Okay, here we go. All right, so going back to trigonometry, now you want somehow to match your example to one of the special trig limits, one of these up here. So that way you can apply that limit to this existing equation. So you're gonna have to be a little bit creative. Do you remember back in trigonometry where you learn all of these trig identities where you have to rewrite them back and forth, etc.? Well, we're gonna be using that skill here today. So then looking at the cosine x over x, I'm looking at this and I'm like, this probably will not change or alter itself to a y minus cosine x. So my goal is to go ahead and somehow modify this into a sine x over x. So then I can replace this with a 1. So looking at this, is there anything there that I can rewrite? There's nothing there that I can do with the cosine x, so I'm going to focus on the tan x, okay, tangent x. Now I know that in trigonometry, another way of writing tangent x is just sine x over cosine x. And then if I look at this a little bit closer, I know that my first cosine x has a 1 underneath it, and the numerator denominator cancels, and voila, I have my sine x over x. That one was pretty simple. So then what am I going to do? My answer is just going to be 1 because I'm going to apply the special trig limit to this example. All right, let's take a look at question number 72. This one is a little bit more trickier. You will probably have to go ahead and think a little bit outside the box. It's not going to be as simple as number 70 where it's pretty straightforward. So as I'm looking at tangent squared x, I know tangent x equals sine x over cosine x. So then I can probably rewrite the tangent squared x as sine squared x over cosine squared x divided by x. Don't forget your denominator. Well, so far there's nothing really I can do except perhaps I can rewrite the division sign. So I have sine squared x over cosine squared x. Instead of putting another division bar, because it's a fraction with a fraction, I'm going to put times 1 over x. I'm going to go ahead and rewrite the sine square x, so that way I have a sine x times sine x. And then if you look at this right here, do you see the sine x over x that I have? That's your special trig, your special trig limit. So then I know that this part, as limit approaches 0, x equals 0, approaches 0, it is going to become a 1. So I'm just going to replace that with a 1. So then what ends up happening is I have a sine x over a cosine squared x. And let's go ahead and apply the limit as x approaches a 0. So what is sine 0 over cosine squared 0? Well, cosine squared 0 is not going to give me a 0, which is awesome. Sine 0, however, will give me a 0. Cosine squared 0 is going to give me a 1. So my answer is going to be just 0. Okay, let's go and take a look at number 58. So number 58 says, find A, and I really should put this in quotation marks so it's not like find A something. Find A so that g of x is continuous. All right, so as I'm looking at this right here, you know that x is greater than or equal to 0, which means x is equal to 0 for the second part. I'm going to go ahead and do 4 sine of 0. I'm just going to plug in the 0 there, over 0, which is 4 sine. I don't want to put in a 0 because it's going to become undefined. So I'm going to try something that's very close to 0. I'm going to say as x approaches to 0. So let's try maybe 0.01 over 0.01. You will get 3.999, which is very close to 4. So then, since I have this as 4, I'm going to go ahead and take that 4 and plug it into the second piecewise function. So with the second piecewise function, I have a minus 2x is equal to 4. And then I'm going to go ahead and solve for this because I have x equal to 0. I'm going to plug that directly. So I have a minus 2 times 0 equals a 4. So a, therefore, is equal to 4. So what does a need to be so that g of x is continuous? A needs to be 4. All right, you guys, if you would like some additional practice, I have this calculus puzzle right here that you guys can go ahead and work on. And it basically says, oh, it says this right here, but there are 27 questions. You can go ahead and practice using this part, and the limit answers are right here in this box. So when you're done, make sure you fill out the puzzle, okay? Pause the video if you don't want to see the answers. But this is going to be the answer. It says neither students knew his limits. Ha, ha, limits, calculus, driving, miles per hour. I know only math people would find this funny. I think it's adorable. All right, you guys have a wonderful day. I'll see you guys next time.